Hey there, so this is part 2 of our video on confidence intervals for a single mean. And so in the last video I asked you to complete the 90% and 99% confidence intervals. So I kind of did the work here, and hopefully you can check your answer. So the first thing is identify your alpha, right? So 90%, alpha will be 1 minus 0.90, which is 0.1, and then divided by 2. 0.05, and then look that up on the table. With degrees of freedom 23, our sample size is 24, so we have to do n minus 1, so 24 minus 1, which gives us 23. And so looking at the table real quick, this shows you the area here. So degrees of freedom, we want 23, and our alpha we said was point. So 2 tells us 0.10, 1 tells 0.05. So that will be here. So 1.714. So that's our critical value. And so then you find the margin of error by doing the critical value times your standard error. And so 1.714 times, we had found this earlier, so just put that in there. And so this is our margin of error. Then the confidence interval, you find that by the lower limit is your sample mean minus the margin of error, and then sample mean plus the margin of error. Now remember, our sample mean was 6.415, so that's how I got those numbers. So 6.415 minus the 0.5188, and then 6.415 plus the margin of error here. And so this is our 90% confidence interval. Do the exact same thing for the 99% confidence interval. So first thing, find your alpha. So 1 minus 0.99, which gives you 0.01 divided by 2. Then look up the table, and now you're doing 99%, so it will be the 0.01 for 2 tails, or 0.005 your alpha over 2. And so that gives us, with 23 degrees of freedom, 2.807. So that's where that number came from the table with degrees of freedom 23. And then do the same thing as we did up here, right? The sample mean minus the margin of error gives you the lower limit, and then the sample mean plus the margin of error gives you the upper limit. So this is our 99% confidence interval. So therefore we have the 3 confidence intervals here, and I wanted you to compare them. So notice the 90% confidence interval is 5.895 to 6.933. So what this means is that based on our sample, we think that with 90% confidence that the population parameter, right, the average hours slept by all ARC students is between 5.895 hours and 6.933 hours. We can say that with 90% confidence. Now, what if we increase our confidence? So 95% confidence interval now is 5.789 and then 7.041. So what happened to our interval? It got narrower, right? So 5.789, 7.041. And sometimes it might help to plot out a line, right? Like if you had, so 5.895, so you can put that, and then your mean, so mu is essentially somewhere in between here, and the upper limit, 6.933. Now what's happening in the second one? What happened to the confidence interval? So now you have 5.789, so it moved in a little bit over here, so 5.789, but notice that it went the other way, so it got moved over here, so it's actually increasing, so 7.041. And then what happens with the 99%? Right? Maybe I should have done this more to the left here. So 5.565 and then 7.264. So and this may be just because of our sample size is not large enough. The larger the sample, the better we're going to be able to approximate our mean. So ideally we want samples that are larger than 30. With our sample of 24, we were so close. So But the larger the sample size, the better the approximation is going to be. And usually, as you increase the level of confidence, your the width of the interval increases. Also, you get wider, and so you can kind of see that start to happen a little bit in here. So, but this essentially, as you're finding these, sorry, I'm trying to not be off the screen here, but so these are essentially the values where we're saying we think the parameter, the population mean, is between this, just based on our sample size, right? So notice that then if we had a larger sample size, like if I had 200 ARC students, I would be able to probably pinpoint this a lot better. So the larger the sample, the better your confidence interval is going to be. All right, now for the next example. In this one, sigma known. So now we know sigma, so that means we're going to go back to using z-scores. In this data, so this is the number of hours the athletes spend on athletic related activities, and you can find this data in StatCrunch. So if you go to StatCrunch, you should be able to find it there under athletic hours. So let me see if I can go to it. So if we go to my data, my groups, and go back to the groups here, we should be able to see athletic activity hours. And so if you open that up, you'll be able to see the number of hours here, and all we want from here is the mean. So go to summary stats, columns, number of hours, and we just want the mean, and compute. And so this gives us the mean is 21.05 hours. So we don't need the standard deviation in this case because the population standard deviation is given to us in this problem. So we just need to make a note of the sample mean. So we can say that the sample mean was 21.05. I guess let's read the problem first. So researchers collecting data about a college athletic conference and its student athletes. A random sample of 40 student athletes is selected and their number of hours spent on required athletic activities for 1 week are recorded. Find a point estimate for the population mean, so that will be the sample mean, which is the mean number of hours spent on required athletic activities by all student athletes in the conference. And then we want to construct a 90% confidence interval from mu. Assume the population standard deviation is 2.3 hours. So this is the part that is important to see that, oh, we have the population standard deviation is 2.3 hours. So we can use that. And so this is what allows me to say, oh, I'm going to use a z-score because I know the population standard deviation. And so find x bar. So this data is in StatCrunch and we found it already to be 21.05. Find the required t-value. So now, the required, critical value. Because now we know sigma, we're going to use the z-scores. So we're going to go over here to the z-scores and we're looking for a 90% confidence interval, right? Is that what it was? 90% confidence. So that means that what do we need to do? So we need to select, so 90%, so our alpha is going to equal to 1 minus 0.90, which is 0.10, and then we need to do alpha over 2. So then our alpha over 2 is 0.05. So now we go to the z-score table and we're gonna go, as we did before, we look at the negative z-scores. So let's go back one page and we're looking for 0.05, which is, usually it's already highlighted here. So that's we have 0.0505 and 0.0495. So is that star is when the area is 0.05, then negative 1.645. But remember, this is, we're looking at our z, that will be the negative and then the positive. So we always take the positive one because our bell shape, right, is symmetric, then we can, when we look at the critical values, so going back to the other picture where is Z alpha over 2 and Z alpha over 2, right? You have negative Z alpha over 2 and positive Z alpha over 2, but we just want the positive one. So it's easier to look up the 0.05 area, so negative 1.645, but essentially what I'm saying is ignore the negative, just take the 1.645. So our critical value then is 1.645. Now calculate the standard error. Let me bring you back to the notebook for a little bit to just kind of explain visually what I was saying, right? So when you have your percent confidence, so you have your Z alpha over 2 is over here, that's the negative, and then you have the positive Z alpha over 2. So when we're looking at a 90% confidence, so that means that you have in the two tails you have 0.10, so that's your alpha. So then alpha over 2 is 0.05. So when we look at the z-score table, the z-score table is telling us the stuff to the left, so it's giving us the negative z alpha over 2, so I just look up 0.05. But my critical value is really the positive, so I just want to look at z alpha over 2, but because of symmetry, right, I can look at the negative, and this value is just negative of that one, so I find that one and just drop the negative. So that's what I was trying to say. Okay, so calculate the standard error. So our error is the critical value, so z alpha over 2 times the standard deviation of the sampling distribution. And in this case, because we know sigma is going to be sigma over the square root of n. So we're going to have the 1.645, right, our critical value, times sigma, which was given to us to be 2.3 over the square root of 40, which is the size of the sample that was given to us. So when you do this on your calculator, we should get 0.598. So that is the error. So now we can construct the confidence interval, and so we can say, right, it's the sample statistic plus or minus the margin of error. So our lower limit is going to be x bar minus the error, and then you're going to have the population parameter, and then x bar plus the error. So we had found our average from StatCrunch to be 21.05, so minus the error 0.598, and then this is estimating our population parameter, so 21.05 plus the error. And putting that on our calculators, we get our lower limit then is 20.452, and the upper limit is 21.648. So we know then the average number of hours that student athletes spend on athletic activities is between 20.45 hours and 21.65 hours if you round to 2 decimal places, and this is with 90% confidence. So what if you did a 95% or a 99%? How will that change your interval? So try maybe a 95% on your own and see what you come up for this. So big ideas here are that when you know sigma, the population standard deviation, then you use the z-score tables as we did before for the proportion. And when you don't know sigma, that's when you use the t-distribution with degrees of freedom based on the sample size. Whatever your sample size is, subtract 1. Alright, contact me if you have any questions.